We have more complex data than ever before. And as Admiral James Sandy Winnefeld Jr. put it, I've got data. What I need is information. More than that, I need knowledge. And more than that, I need understanding so I can take action. That was 9 years ago, addressing a group of military analysts. But in this age of big data, his message is even more relevant. How do we go from data to confident action? We'll start by seeking guidance about how to use machine learning and modern methods to find insights in data. I'm Tom Donnelly, your panel facilitator. It's my honor to host a group of experts with vast experience wrangling complex data, building useful models, and leading machine learning initiatives in the defense space. We'll begin with a keynote presentation from Dr. Laura Freeman of the Hume Center for National Security and Technology at Virginia Tech. Then Dr. Freeman, Dr. Raymond Hill, and Dr. James Wisnowski will participate in a panel discussion. We'll all benefit from hearing the real-world examples and applications they share today. As you listen and learn, we urge you to post on social media using the hashtag #StatSpeaking. Laura Freeman conducts research that brings together cyber-physical systems, data science, artificial intelligence, and machine learning to address critical areas of national security. She is a research associate professor in the Department of Statistics and leads a research program in artificial intelligence assurance for the Commonwealth Cyber Initiative. Here's her talk on demystifying machine learning and artificial intelligence for the defense community.
Hello, and welcome to my basement. I'm happy to be with you today talking about the demystification of machine learning and artificial intelligence for the defense community. The talk today is really divided into 3 parts. The first focusing on the guidance that the federal government has given us and how that makes it so critical that we figure out how to demystify these algorithms. The second provides some baseline kind of concepts of what artificial intelligence is and how statistical thinking, statistical engineering, and statistical methods and tools are going to be critical for that demystification. And then finally, I'll give a few research problems that we're currently working on and how we're using statistical tools to tackle them. So let's dig in. We'll start with 2018's DoD Artificial Intelligence Strategy. The department was one of the first to issue guidance on artificial intelligence from the federal agencies, and it focused on delivering AI to key missions quickly and efficiently. And so that when the strategy highlights things like decision-making, preventative maintenance or predictive maintenance, and situational awareness as key missions where AI will have large impact to the department. One of the things I think is very interesting about the strategy is that part of the strategy is actually a little bit of the implementation on how they hope to achieve this speed and efficiency. And that's through this scaling of a common foundation. So think AI testbed, where you have exchange of models and tools and data, which I think has been adopted by a lot of folks in the federal government. They also express the desire to cultivate a leading AI workforce and engage with commercial, academic, and international partners in this effort. But the area that I want to spend the most time talking about is in this last bullet, leading in military ethics and AI safety, because those are things that I think are critical for understanding how our algorithms are working in that demystification. So under that area of leading in military ethics and AI safety, I, of course, tried the favorite statistics data science trick of making a word cloud of all the words in the document that related to this. It was a little bit of a fail here because it wasn't quite long enough. And in fact, the first version of this probably should have left, but it had the word will in there 19 times. And so it was really just the big will. So you can, that's interesting in emphasizing how all of this is forward looking for the department. But the executive summary had some great words that I want to highlight and I think are critical for that demystification. So research and development of AI systems that are resilient, robust, reliable, and secure. All of those things suggest that you understand exactly what your algorithm's doing, why it's doing, and you can predict what it's going to do in the future. And that it's explainable AI. And then a part that I like coming from the test and evaluation community in particular is that we need to pioneer approaches to AI test evaluation, verification, and validation. And that those will be new approaches. We'll talk about some of those today. And then they also emphasize partnerships and transparency in their approaches to AI. So the Department of Defense is not the only organization to have AI strategies and priorities out there. A few others that I flagged because of their how they all kind of coalesce around these concepts is the Department of Energy's and NIST, and then just a couple weeks ago, the the intelligence community put out an artificial intelligence ethics piece. And so you see the same terms over and over again: secure, resilient, robust, equitable, objective, transparent, explainable. Really, what we're hearing from the federal government is that we need to be able to deliver these things for them to be able to adopt the wide-scale use of AI. And so a few themes that I want to highlight is that the government is not just worried about the predictive capabilities. They want to move beyond that and focus on these concepts of robustness, resiliency, and explainability. That data matters, quality data matters, and scientific understanding matters. And that we need research to accelerate our capabilities. Specifically, we need the concepts of trust and assurance in our AI algorithms. And then, of course, AI test evaluation, verification, and validation is a research priority, and test beds as an enabling mechanism. I really love this quote from the National Artificial Intelligence R&D Strategic Plan, which I didn't summarize on the previous slide. But it highlights the unique opportunity that test beds provide coming from the government to industry and academia to do research. And that the government they own the data, and they own the sensitivity of the data and the quality of that data. But test beds provide and through these appropriate filters, the ability to tap into the academic and the research community and industry with this data so that they can start to develop there. And so I, of course, am very passionate about unique research opportunities for students as well. So with that as the backdrop, I want to talk about what our goal is for today. And really the goal from my perspective is to illustrate how statistical thinking and the supporting processes and tools provide a framework for demystifying machine learning and artificial intelligence. And I highlight the word framework in particular, and you'll see why as we go through this, but there's so many variations of machine learning and artificial intelligence, and to try and demystify them all as a whole is not really an achievable task, but understanding the principles that lead to that will be important. But first, when we talk about artificial intelligence, let's define what we're talking about. So I'm quoting two very smart people here in that definition as opposed to making up my own. Dr. Don Launchbury, who is the former director of I2O at DARPA, had a great presentation on artificial intelligence where he calls artificial intelligence a programmed ability to process information. And that there's different dimensions to artificial intelligence, including perception, learning, abstraction, and reasoning. And that we're currently, he also defined 3 different waves of AI. So handcrafted knowledge, this is kind of expert-based, rule-based models of the past. What he defines as our current state, albeit this was a few years ago, in terms of statistical learning. And then a future state, which allows for contextual adaptation based on known models, mechanisms, and those types of elements potentially combined with statistical learning elements. Dr. Allison Wilson from NC State shared a different perspective, but still similar in terms of what AI is, where she focuses on machine learning and data mining. So machine learning focusing on prediction based on known properties learned from training data, and data mining trying to discover new things that we were previously unknown. And says that what is being called AI today is really data mining plus machine learning rebranded. So I'll give you an incomplete taxonomy of kind of what I would call those first 2 waves of AI and correlate those to what Dr. Wilson was saying as well. and that there's the reasoning, kind of the fully deterministic programmed version of AI, where you've got agent-based systems that, or linear programming optimization, those kind of approaches, versus the statistical learning approaches, where we can bend those generally into a few broad classes: supervised, where we've got labeled data and we're doing predictions; unsupervised, where we're trying to learn new things and we don't have labeled data; and reinforcement. And then a lot of the emphasis, I'll do a call out to the neural networks bubble here, because a lot of the emphasis in recent years has been on these deep neural networks, which have different types of approaches: variational autoencoders, generative adversarial networks, convolutional neural networks. And so you see all those different types of variations. So the space, this incomplete space that I've highlighted here, is quite broad. And so to really understand each one of these algorithms is going to be a different approach. So why do we need a framework? Well, there's not only all those different types of models, but there's lots of different types of data. We'll talk about how different data sets have different properties a little bit later on. There's different goals behind your algorithm. So you could be wanting to just classify things, or you might want to forecast future values. You might want to optimize. All of these goals will be best suited to different types of algorithms. And then not only are there all the different types of algorithms, but we often cannot combine them in unique, different ways. So we might do a bunch of averaging, fit a bunch of models independently and average them, or we might build them sequentially. We might stack different models. All of those choices lead to different implementations. And then finally, what makes a good algorithm really depends on the intersection of all of this. So when you say, we need to find a way of figuring out explainable AI, how we do that is going to be dependent on each one of these kind of independent situations. So that's why I think we need a framework, because this is going to be a complex problem. But I'll say from a statistics background, statistical thinking has been critical in kind of solving these complex problems in prior research as well. So one of the first things that comes to mind for me, coming from Virginia Tech, is agriculture, and how statistical thinking and split plot designs were key to understanding how to optimize crop yield. Another one, manufacturing, the total quality management, Lean Six Sigma era, took lots of different statistical methods and tools, strung them together in unique and innovative ways to solve manufacturing challenges and make products more robust and secure. So exactly what we want for our AI algorithms. And then in my former life, testing military systems. Military systems can be some of the most complex systems in terms of the software that they implement. This is a picture of the F-35, enormous amounts of software that go into that system. So while not machine learning, still a very complex system to understand how it's going to work in all sorts of different operational scenarios, and statistics and design of experiments have provided a solid basis for understanding those systems. And then finally, the most complex system I can think of is a human. I've shown a picture of an EEG here, so measuring brain patterns, which is quite complex, and statistical and experimental protocols have been key in those types of studies, as well as things in terms of like what makes successful teams, what makes successful leaders, the development of survey instruments and data collection. There has helped us solve those really challenging problems and the source of enormous amounts of variability, which are, the variations between us as humans. And so I think there's a good reason to look to all of these as kind of what is the framework that supports the eventual demystification of AI. And so that framework I'll lay out here in terms of statistical thinking and statistical engineering. So statistical thinking, this is originates with Edward Deming, and of course we're standing on the shoulders of giants here and thinking about this. This specific definition comes from Ron Snee in a total quality management paper. But basically what statistical thinking is kind of a strategic philosophical approach to problem solving and thinking, where the core tenets of it are that variation is present in all processes, and that all work is conducted in a series of interconnected processes, And then the version that Ron uses in that statistical engineer or that total quality management article is that reducing variation improves quality. But that was the problem of the day they were trying to solve. I think my more kind of broad interpretation of that is really not that just reducing variation, but it's understanding, characterizing, explaining variation, and then reducing if that's the right choice. Sometimes it's just enough to know that variation exists and that you know exactly how much variation you can expect. Thinking of humans again, yeah. We can't reduce variation. Well, in some situations. But anyway, so it's that leading to successful outcomes that we want. And by understanding that variation, we can get there. So that is at the very strategic level. And then, of course, at the operational level, we have the tools, the methods that we use to do that. So we have our favorite software packages, of course, JMP and R and all the other packages out there. We have design of experiments, we have regression, we have all the different machine learning and AI algorithms that I just presented. And those are at the very operational, like, what do I do? But in between that big picture thinking and the actual operational, I'm going to go, use a control chart, there's this tactical, managerial, kind of more process-oriented piece that's needed. And I'll pull from ICEA, the International Statistical Engineering Association, here and talk about statistical engineering is that connective tissue, the thing that gives us the process to get from the strategic thinking to the operational. And so I've got a picture from the ICEA website here that really focuses on kind of the general process, and that every problem is going to require a unique implementation of the solution. And some examples that I'll give in terms of my mind of executions of that are, of course, the Six Sigma DMAIC process, and then coming from testing military systems, the test and evaluation framework is really a execution in statistical engineering. In terms of you have to go through all these steps to understand how to test a complex system. Really problem identification is the core piece that has to happen first. So the rest of the talk, I'm going to talk about 3 different problems that I've identified in my research and my work with my collaborators, and talk about how we're using statistical methods to tackle those as a basis for the demystification of machine learning and AI. So the 3 problems that I'll hit on are: how do you understand the operating envelope for an artificial intelligence system? And how do we characterize that? And we'll start with computer vision because it's a really fun pop culture almost machine learning challenge. Next, we'll talk about understanding model robustness and the intersections of model robustness and the data that's available. And then finally, we'll talk about optimizing. I don't mean like in the literal sense of a strict mathematical optimization, but how do you get the right configuration of your machine learning models for the problem at hand? So those are the 3 problems that we'll talk about, and they're in varying levels of done in the research, starting with the most immature to the most mature. So computer vision challenges. These are well known for computer vision challenges, that if you have an image and you add some noise, all of a sudden your classification changes dramatically, or you rotate the image slightly and you go from a cat to guacamole just by shifting the head in that way. Or in this one, they're putting a picture of a toaster in with the banana and changing the classification based on what's surrounding the object of interest. So these are fun toy examples. But I really want to know how to define the operating envelope of my model for kind of more complex situations than just cat classification. So the data set we're going to pull on from here is one actually developed at a university in Denmark, the AU air label data. And so you can see a picture of that on the left-hand side of your screen here. It's a traffic circle in Denmark. Is the image that I'm showing. And you can see it's a labeled data set, those red boxes, the bounding boxes drawn around cars and bikes and trucks in this data set. And it also has a lot of metadata associated with it. And that metadata, I think, is going to be key for getting to concepts of explainability and understanding where models can be used in the future. And so the question is, well, if we train an algorithm based on the data here, how will that work when transferred to a new location? So if it transfers to the traffic circle on Virginia Tech's campus, it looks fairly similar, but will it work there? Are there differences that would make it not work? And how do we know? Or the traffic circle in Scottsdale. Or if we just want to use it a four-way intersection, how will our algorithms work? And how can we know that in advance is really where we're going with this research. And so the tools that we bring to bear are things like exploratory data analysis. So here's the AU Air data set. You can see it's not just the traffic circle, they also have a parking lot and a field that they've collected there. And we can look at when they collected data. So here's information on the time of day, and you can, this is a scoped out versus a drilled in view. The reason that we're really interested in this one is that because of the time of day, the altitude of where the UAV is, we think that will drive different levels of contrast, which could give our algorithms a challenge here. And so you can imagine if you're at noon, sun straight down, and your UAV is, regardless of altitude, you're going to have a very similar kind of perspective on the ground. Whereas if it's 9 a.m. and the sun's coming in at a more of an angle, you're going to get different shadows and contrast. And so these are the types of kind of theories that that we're hypothesizing about that could drive model performance and then allow for us to understand transferability into new domains. So we can look at the velocity, the altitude, how big the bounding boxes are, which could give us some insight to, well, now if we move to a double trailer 18-wheeler, how well will that do? Were there any of those there? Those kind of questions. Also as a function of altitude, right? Because of different altitudes, different car sizes, that might help us understand how well the algorithm's doing. And so the approach that we're taking here is we're looking at kind of the coverage of our algorithms in the input space domain. And then we're going to correlate that input space domain to the output space, see if we see unusual trends, and then revise back in terms of how we define the space so that we understand that transferability. So here is one of the metrics that we're using, combinatorial coverage, which just looks at, based on all the variables, we're just using the metadata to get started, available, what combinations are covered. And so we define the universe as everything that's in the data set. So at a 1D strength, all of the combinations are covered. But when you start to look at strength 2, which would be two-way interactions, so you can see the missing ones. So in location 2, we don't have any morning data points. In location 3, same thing, no morning data points. So only location 1 has those morning data points. And so you can start to see, as you go through these combinations, a lot of unbalance in the data set. And that could give us some indication for how we might expect this to transfer to new conditions, whether depending on the coverage there. And so there's also the output space here. So here's where we're using statistical emulators. This is actually simulated emulator data. This is not for the AU Air data set yet. We're still working on having graduate students go through and check labels. And in fact, looking at bounding boxes and all those things to make sure they're correct. And so here, this is just what we're planning to do next once we have those data sets correct. As you could imagine, based on those 5 different time of day bins versus the 2 different time of day bins, fitting kind of your mean classification error and a standard error around that. And so how we would use these emulators is looking at that plot on the left, which hypothetically shows altitude versus time of day. If you saw a contour that didn't have much change to it, that's evidence that, that metadata is maybe not interesting for classification. And therefore, it's probably okay to not have complete coverage, or we don't need to fill in the data there, or that might help us understand how well it will transfer to new altitudes and times of day. But if you look a little bit at what would be the lower altitude setting, on that plot, you can see all of a sudden that we do see contours that are changing a little bit more rapidly. And that would suggest something along the lines of, okay, well, in the morning, at a lower altitude, I'm seeing, an angle at that's driving an angle, essentially in contrast to the sun. And so maybe we're getting shadowing there that's causing classification errors. And so that would help you understand whether you can or whether you need more data to train, or whether you could use this in environments that looked like that or not. So we have lots of big plans for where we're going in this research. So given models trained on various data sets, we want to be able to answer kind of all the questions here. Are there types of models that tend to perform well in new environments? So to do that, we have to be able to characterize the environment as part that input data set, and then look at the new environment and characterize it there, and then understand whether the model performs well. Are there models that will transfer with minimal retraining? And then also, what characteristics of your training data are needed to facilitate that robust transfer? So those are all the different ways that we're looking at this data set and many others in that research. We also want to understand when, if you're using a model, say online, and it's just deployed out there, if anything in your environment changes that makes it so that you might want to think about recertifying your model. How do we know that the environment's changed by that much if we're in a new space? And how do we know we need to recertify? And then kind of from a decision maker perspective, we think all of these things will help us understand, given the AI testbed concept with all of our models hanging out in the cloud with different data sets, what model is best, and if that model is best, just use it. Or if there could be some kind of optimal orchestration or ensembling of models to meet a new target domain. Invest in fine-tuning by taking a model that exists and then freezing some layers and then retraining some of the other layers with the target environment. Or quantifying risk, understanding when we really just do need more data in the target environment to retrain. And the picture on the bottom here too is meant to show this is not a one-size-fits-all solution. What these are showing you is the universe of data. S is kind of the source data that our model was trained on, and T is the target. And so these show different set overlaps that we're interested in investigating as we go through that. All right, so that brings me to the next problem, which is understanding how to select a robust model based on available data. So as we've gone through a lot of these data sets that are publicly available, we've noticed that they're not necessarily well distributed in terms of an experimental design sense. You often see very heavy biases to one set of categories. So in our AU Air data set, there are lots of cars, but far fewer trucks and bikes. And so you see that systematic bias or not necessarily systematic bias, but you see that imbalance creep up in lots of kind of machine learning data sets. And so we want to understand, how do we go about selecting a model that's going to be robust for that? So here we're taking a mixture experiments approach. And so you can see on the right-hand side of this slide, I've got a mixture experiment that looks at trucks, bikes, and cars. And it's a slightly modified simplex centroid design in that you can see the cars is not quite at 100%. We nudged it off 100% and then put 1% in trucks and bikes. And so the first 3 rows really show a really highly imbalanced. And then you can see rows 4 and 5 show balance in 2 of the objects. And then, 4, 5, and 6 show balance in any 2. And then 7 and 8 are balanced across all 3 objects. And so that's the composition of our training set that we're looking at here. And then we're going to fit different models, and we'll have a test set that either is the exact same layout or composition as our training set, or we'll reverse it. And by reverse, we mean if we were highly unbalanced before, we'll go to balance. And if we were balanced in 2, we'll flip who the balanced in 2 was. And then we look at the average AUC, area under the curve, for a ROC curve as our metric here, where that's just averaged across cars, bikes, and trucks. And so this is a simulated version of that, because we don't have it for the AU Air data set yet. But the goal would be to be able to show that based on the 2 models that you see improved performance, and then whether there's any interaction between the improved performance based on the composition of your testing and training set. And so also we've had a grad student working on this project, and he's been looking at mouse embryonic stem cell data and compared XGBoost and CNN and had great success there. That's actually where these simulated values came from. I just wanted to keep it to one data set example here. So in future directions, we need to focus on making sure that we're We need to account for the training set size, because some models are going to do well with smaller training sets and others will not. So we need to make sure we're not biasing our results based on that, or at least we're characterizing our results based on the training set size. And we need to be able to adapt the measure to the value of training data augmentation. And so, like, if we were to take that AU air data set, those images, and add weather effects onto them, or rotate them through different spaces, or shrink or stretch, that's what I mean by augmentation. It would be great to have these types of approaches to show that value. All right, the third problem that I'm going to talk about is selecting complex configurations for machine learning models. So this is when coming back to the concepts that you can put things together in ensembles, or orchestrate them, or build layers up in your neural networks, or deeper and deeper. How do you pick the right structure of your machine learning model? And so here we're using what I'll say loosely kind of is inspired by robust parameter design and Taguchi methods, but we really more fell into that backwards. And so that's maybe a lesson learned, that we should leverage those types of tools and techniques. But the goal here is to cluster documents, and the angle being to study technology emergence. But first off, we really just want to make sure we cluster things correctly. And so, and this was the system ultimately will be used by many diverse users, not just the analysts playing with it as well. So we want to make sure everything that we do is robust to that. So we have different types of documents, publications, and patents, and depending on whether the user does a search for computer science versus federated learning, you're going to get different volumes of data back. There's all sorts of representations from the natural language processing community that we can use. There's different types of clustering, and then the outcomes are going to be how we compare these different methods. So I call it an adaptive sequential design process, but we adapted as we learned. And so this could be a little bit more purposeful. But because we're running short on time, I'm just going to show you kind of the analysis that we did. So here's the select analysis. We were comparing between doing principal component analysis or principal component analysis combined with the UMAP. And sometimes these simple visualizations are really enough. And so you can see here we did a full factorial design. I skipped over that piece. And what we've got across the top are different representations, from BERT to Doc2Vec to Cent2Vec, SciBERT, SPACY, TF-IDF, different representations that we might want to implement in our system. But here, the decision that we made is that PCA UMAP did better across the board with no noticeable degradation, so we went with that. There were these unique run times. We also, want this to run pretty fast, so we don't want these run times. And through just a simple exploratory data analysis, we were able to figure out if you made your min samples and your min clusters too small, you got these really long run times, and so don't do that. And so once we understood the data well enough, we actually got rid of these run times because we understood why they were happening. We can start to think about modeling it. I forgot about this one. But this one really just suggests that we're looking at runtime as a function of a lot of different parameter settings here. And really what this is showing is that runtime is dependent on sample size and not much else. So great news. It's going to be, runtime should be okay as long as we got rid of those high outliers. And then simple statistical models go a long way. So what I'm showing here is it's centered on Doc2Vec. And you can see in that first panel, we have the size of the data set, and then Doc2Vec is my model selected, and the rest is a bunch of tuning parameters. Don't worry about those. But you can see that my performance is invariant to the sample size of my data for Doc2Vec, which is a nice thing because we don't know how many queries the user is going to be sending back. Whereas when we look at our Cent2Vec model, which did better in small sample size situations, you can see though that it doesn't do as well when you get into larger sample sizes. So those kind of approaches allow you to make a design choice between, well, do I think most of my analysts are going to be running small samples or larger? Do I want it to be robust? Or do I kind of optimize and kind of ensemble my two methods in some way? Or orchestrate, string them together. And the final thing that I'll call out as useful in these types of decisions is that doing these model statistical emulations or simple linear regression, well, multiple regressions here, but doing statistical analyses on top of these experiments run on machine learning data gives us definitive ways to decide what matters and what doesn't. So here I can show that a lot of these parameters towards the bottom have very small effects. And so I can set them to whatever value I want. I can optimize them. They're not going to affect my performance in terms of how well I do my clustering. Whereas the model and how long I allow UMAP to time out for is going to have a huge effect. And so I should focus on making my model, focus on those parameters when picking my model settings. All right. So I want to conclude with thinking about moving towards a framework. So we've talked about some statistical tools and methods that allow us to understand our algorithms and show that with data today. But we really haven't talked about the framework because I'm still putting it together in my head, as well as running through those examples really provides the basis for that. But one of the things that is critical for a framework and how we think about this framework here actually comes from the DoD's test and evaluation, operational test and evaluation community, where they think about how do you measure success. And so one of the things we've been thinking about when we start thinking about artificial intelligence and machine learning algorithms is how do we measure success and does that change? And so, of course, I think measures of effectiveness and measures of suitability and survivability still persist. We'll still need those. But maybe we need to start thinking about additional measures that tell us how well that algorithm is doing. And those could be task success and completion. So not all that different from any algorithm today, except you definitely want to measure the algorithm. Or they could also be algorithm specific. So depending on how much knowledge we have of what it is, there's the black box, gray box, white box, full understanding to no understanding will drive how much we can measure about that and is an important consideration in terms of how we test these algorithms and complex systems moving forward. Another dimension that we've contemplated is measures of human and agent teams and how those come together to maximize the combination of both our humans and our machine learning and AI algorithms. And so maybe we need to be thinking about measures there to add to our frameworks. And I'll conclude with kind of some additional thoughts in terms of moving towards a framework and process control. Because one of the things that in my mind is going to be very different is that test and evaluation and understanding of our systems doesn't stop when the algorithm is fielded, because our environments that they're used in are going to change, and there will be events that maybe make us think, oh, we need to re-baseline and understand that. And so this is a model that we've been iterating on with some of our collaborators at Purdue on how to modify kind of the V&V process, thinking that in V&V early, we need to be a little bit more agile, having quick iterations through that. But then once we deploy, there's going to be possible events. Say you've got a mission objective change, something that was deployed in space to look at fires in California now needs to go look at ice melt in the Arctic. Does that change what you need to think about for your algorithm? Or there's a degradation in the hardware, software, you lose power. How does that affect things? And so those kind of things we might want to have specific checks in place, or an adversarial attack. But also the concept of quality control and kind of maintaining awareness of how our algorithms are doing as they just go from day-to-day operations. So I think the field of process control is going to play in there. And then the P part of this model, the feedback loop, is that then we'll need to maybe update our models, retrain to move forward. And so with that, I will conclude and say thank you for your time, and I look forward to the panel discussion. I think demystifying machine learning and artificial intelligence is going to require a framework. Statistical thinking, process methods, and engineering are going to be critical for that. But I also I don't want to end without acknowledging my collaborators on these. The thoughts that I pulled from today span projects with collaborators across 5 or 6 different universities and departments ranging from computer science to psychology. So while I've emphasized the statistical thinking part, clearly this requires an interdisciplinary approach. Thank you.
Thank you for your insights, Laura. I especially like your comments on leveraging design of experiments with machine learning and artificial intelligence. If you'd like more details on the fundamentals of machine learning and artificial intelligence, as well as a holistic approach for using these methods, you can find more details at jump.com/holistic. Let's take a 5-minute break. We'll be back with a follow-up panel discussion.